Good morning, everyone. Today we're exploring how data travels across networks. Specifically, we'll look at the difference between perfect and imperfect channels and how ARQ, automatic repeat request, acts as a safety net for all of our data. Talking about channels, there are two types of channels, noiseless channels and noisy channels. Imagine talking to a friend at a soundproof room. That's noiseless. Whereas, try talking to the same friend at a loud concert. That's a type of noisy place. Like this, channels also have noiseless channels and noisy channels. Noiseless channel is a perfect connection between a sender and a receiver where the sender can send frames to the receiver seamlessly without any issue. This is called a noiseless channel. Noisy channels are the reality where bits get flipped, frames get reversed, and so many issues can happen while frames are sent by the sender to the receiver. And there are many error control mechanisms which help to avoid or to at least find out if such discrepancies have happened. These we're going to learn going forward. To handle such errors and discrepancies that happen in noisy channels, ARQ is used, which stands for Automatic Receive Request. This ARQ is used to handle errors by making the receiver send an acknowledgement back to the sender. When the sender sends a frame and the receiver successfully receives it, it is forced to send an acknowledgement, which once the sender receives, the sender sends the next frame. There's a timer which starts the countdown as soon as the sender sends the frame, and if the acknowledgement is not received within the time frame, the sender resends the previous frame. There are many types of such ARQs which we'll study moving on. The first and simplest error control protocol is the stop and wait protocol. In this, the sender transmits exactly one frame and waits for the receiver's acknowledgement to come. And once the acknowledgement comes safely, the sender transmits the next frame. Let's say the acknowledgement does not come, the sender retransmits the same frame which it had sent before and then waits for the acknowledgement to come. Like in the diagram, you can see the frames and acknowledgements are sent and received, and if the timer runs out, the sender still retransmits the same frame. A normal transmission goes this way. A sender sends a frame and waits for the acknowledgement of that frame to come. Once the acknowledgement of the sent frame comes, it transmits the next frame and waits for the acknowledgement of that frame. The second case is the lost frame case, where the frame 0 that was sent by the sender is destroyed in transit. Thus, the receiver never receives it and thus does not send an acknowledgement. So once the timer runs out and the sender knows that the acknowledgement has not been received, so the sender retransmits frame 0 and waits for the acknowledgement of that to come back. A very important case in stop and wait ARQ is the case of lost acknowledgement, where the sender, that is host here, sends a frame which the receiver receives and sends an acknowledgement where the acknowledgement gets lost. In such a case, the sender waits for the timer period wherein the sender waits for the acknowledgement. But when the acknowledgement does not come, the sender resends the same package. But then, since the receiver has already received it and sent the acknowledgement which has got lost, thus the receiver drops the copy, which is the duplicate that it gets, and resends the acknowledgement one which it had sent earlier. Thus, it keeps only one copy of the message that was sent. Another important case for stop and wait is the late acknowledgement case, where the sender sends a frame and the receiver receives it, and the receiver sends the acknowledgement for that case, but the sender receives the acknowledgement so late that by the time the timer has expired, due to which the sender retransmits the same frame, as in, let's say we send frame 0 and the receiver receives it and sends acknowledgement 1. When the receiver, by the time the sender receives acknowledgement 1, the timer has expired. So here, as you can see, the sender resends frame 0 thinking that the receiver has not received frame 0, and on the receiver side it has received two frame zeros. So thus the duplicate one of the frame 0 is removed by the receiver, and as it gets the late acknowledgement from the receiver, the sender, thus the sender moves on and ignores the second duplicate ACK. Thus, frames are wasted in late acknowledgement. Thus, it's not usually used. Another type where ARQ is used is called the go back N ARQ. In this, It uses the sliding window concept. How is this different from stop and wait? In sliding window, instead of sending one frame at a time, it sends multiple frames at a time, which is called the window. Let's say the window size is 4, so 4 frames are sent consecutively without waiting for the acknowledgement of the first frame to come. Thus, 4 frames can be simultaneously sent. But the issue in this is that, let's say any one of these frames gets corrupted or the acknowledgement is not received, the sender has to resend all of these frames together. Thus, as you can see in this, the sender sends multiple frames here. 4 frames are sent by the sender, and even though only one of the acknowledgements is not received, the sender retransmits all of the frames again. Thus, this it's a very rigid format in which it only accepts the frames arriving in correct order, and all the acknowledgement of all of the frames sent should come on time. Thus, this is a very useful concept for sending multiple frames at the same time. Just like stop and wait, this too has a lost frame case. In the ideal scenario, let's say the window size is 3, and thus the sender sends frame 0, frame 1, and frame 2, and thus it expects that acknowledgement 0, 1, and 2 should come in the same order. Thus, when it receives it, it can send the next frames that are frame 3, frame 4, and frame 5. This is the ideal scenario. But in the loss frame case, where you can see here, the receiver gets frame 2 instead of frame 1, wherein frame 1 should be received before frame 2. Thus, it discards it because the receiver expects that frames should come in order, as in frame 0, frame 1, and frame 2. Thus, the sender goes back and resends both frame 1 and frame 2, since in this either 3 frames are either resent or 3 frames are collected together. This also has a lost acknowledgement case, wherein, let's say here the window size is 4, and it transmits all these 4 as in frame 0, frame 1, frame 2, and frame 3 together, and the acknowledgement for one of these frames is lost. That is, as you can see, the acknowledgement is not received by the sender. Thus, in this case, due to it being a sliding window protocol, 4 frames are sent together. So thus, even if one of the acknowledgements is missing, the sender has to send all 4 frames again. Thus, it ignores the first acknowledgement that it has received and continues to retransmit each and every one without issue. The third type of protocol is called the selective repeat protocol. Earlier, we've seen protocols where one mistake forces the sender to restart everything. That's like dropping one egg and throwing away the whole carton because of it. This is very inefficient. And due to this, selective repeat ARQ is a very high bandwidth saving type of protocol. Inside this, it's very efficient and very complex because even if one frame goes missing, it still accepts the bunch and buffers the out of order frames that follow it. This also uses the concept of negative acknowledgement. What is negative acknowledgement? Negative acknowledgement means that even that instead of just staying silent, the receiver can be proactive. That is, it sends a negative acknowledgement. It's like an SOS signal that tells the sender exactly which frame went missing. It's like a sort of direct order that tells the sender to send me frame 1. Example, if frame 1 goes missing, it tells the sender to specifically give frame 1 again. That is a very impressive feature of the selective repeat ARQ. And the sender retransmits only the specific frame that was lost, not the entire bunch. This makes it the most efficient and best ARQ that has come out till now. A normal transmission of this happens in the way that the sender transmits number of frames that are present inside the sliding window, which can be any number like 2, 4, 5, 6. The receiver sends individual ACKs for each and every frame that is received by the receiver. The sliding window. Here, the sender and the receiver both have a sliding window, which is not the case in the previous one. A very famous case is the loss frame case. Inside the loss frame case, a frame out of the number of frames that the sliding window sends, a frame is lost or can be buffered or is not received by the receiver. In this, the receiver explicitly sends an NAK, which is a negative acknowledgement. The sender gets the negative acknowledgement, so it acknowledges the acknowledgement that it has received an acknowledgement which shows that the receiver has not received a frame, which was not received, which it should have received. Thus, due to which the sender resends the frame whose acknowledgement, whose NAK was sent by the receiver. So the sender retransmits the frame and it organizes the data in the buffer the way it should have come. Another important case for the selective repeat ARQ is the late acknowledgement case. As you can see inside this, the frames 0, 1, 2, 3 are sent, and when frame 0 is resent again, the acknowledgement for frame 0 gets very delayed. And in such delayed acknowledgement cases, the sender selectively retransmits only frame 0 since the acknowledgement has come very late. But since the receiver has actually received frame 0, just the acknowledgement has been received by the sender really late. So when the receiver gets frame 0 again, as the sender has resent frame 0, the receiver recognizes that this frame has come twice. So it drops it and resends acknowledgement 0 to clear the sender's window. Thus, it discards the extra frame 0 that has arrived. Due to this, the sender and receiver both receive only one copy of frame 0. It does not it does not include two frame zeros. And unlike other protocols, not the whole window is retransmitted, only the particular frame that has become late has been retransmitted. Thus, this saves bandwidth and time. Now let's compare all the three ARQs that we have learned till now. Stop and wait, go back in, and selective repeat. As we know, stop and wait can only transmit one frame at a time, which was the biggest issue with it. Whilst go back in and selective repeat use the concept of sliding window. In sliding window, the sender can transmit multiple frames at one given point of time. But if we see the receiver's window side, stop and wait always had one, but go back in has only one, which means that the sender can only track one frame at a time. Whilst in selective repeat, the receiver has the option to track multiple frames at a time, which means it has a buffer which can show the amount of frames it has received, which means it can see one frame before, it can see multiple frames before and after which it's supposed to receive. Even if we see the acknowledgement, stop and wait only gives individual acknowledgements, whilst go back and can give cumulative, but this is an issue with selective repeat, where acknowledgement for only one is sent at a time. But while doing retransmission, go back and let's say even if one frame out of the 10 frames sent are not received by the receiver, in go back and you have to retransmit each and every frame again, which is a very big issue in go back and whilst in selective repeat, the frame which has been lost has to be retransmitted. Thus, it saves a lot of time and bandwidth. While stop and wait is very inefficient, go back and except apart from the bandwidth issue, go back and is nice. But selective repeat is the best one out of these three, as it offers the best features in terms of sending, in terms of utilizing the bandwidth and saving time. And since it only needs to transmit one frame, even if any frame is lost, or even in the case of lost acknowledgement or late acknowledgement. Thus, the best one is selective repeat. As a conclusion or grand recap of what everything we've learned today is to bring everything together, what we've explored, or for the evolution of reliable data transmission at its very core, ARQ protocol attempts to solve the exact same problem. Now, how do we guarantee that the data sent across an unpredictable noisy channel, which is how in real life channels are usually very noisy or not noiseless as how we assumed in earlier times. Nowadays, real world examples are seen where channels are noisy and thus we need better mechanisms to handle it. Thus, how do we send data across an unpredictable noisy channels and hope so that the receiver receives it intact and in the correct order in which the sender has sent it? Thus, we started with stop and wait, which gave us the baseline mechanics of the acknowledgement and timeout of what the concept of acknowledgement and timeout is. But as we saw, it underutilizes the amount of bandwidth it basically uses. To solve this, we introduced pipelining with go backend by using a sliding window, which is the concept where we send multiple number of frames together and go backend keeps the channel full and drastically improves throughput, but it does so at a cost, which is its reliance on cumulative acknowledgements. which means, let's say even if a single frame out of all the frames that you've sent does not go through, or the acknowledgement is delayed, or it just does not reach there, the entire window has to be retransmitted. Thus, it wastes bandwidth and unnecessary transmissions. Thus, we made selective repeat, which offers the highest channel efficiency by isolating and retransmitting only the lost packets. The trade-off is that it's very complex as compared to go backend, and it requires memory overheat at both the sender and receiver, as both the sender and receiver have a selective window, and it has a buffer to reassemble out of order frames. Transition to, and now we can see about the real world implementations. Now, while these three are textbook models which are crucial for understanding network theory. But how are these actually used in real world today? In modern networking, these protocols are rarely used and are rarely used in their pure isolated forms. They serve as the foundation for much complex systems like modern TCP, or which is the backbone of our internet, which we use every single day. And it mainly uses go backend, which is an advanced hybrid modern TCP. Implementation relies on extensive called TCP SAC, or selective acknowledgements. SAC allows the receiver to tell the sender exactly which discontinuous blocks of data we received successfully. This beautifully blends the low overhead of go backend's cumulative acknowledgement, which is the concept where all the acknowledgements have to be received, and let's say even if one is not received, it retransmits all of them. This is a problem is getting solved. And there are very high level topics like HARQ and BDP. Thus, the boundaries of wireless communication with 4G, 5G, and beyond that standard ARQ isn't enough to handle. Thus, there are many concepts that are more to learn and more to see. And here we end today's lecture.